Okay. So, question 2. Rotating, so, okay. Circular field in the area of A, resistance R is an external uniform magnetic field, B, Z direction, okay. And at T, the magnetic field is perpendicular to the plane of the loop as shown. The loop is rotating constant. Okay, so it's number 2, okay. Omega, period T. The magnetic flux of the loop is, okay, yeah, this is important. Flux equals BA cos omega T. Okay. Yeah, that makes sense. The value of the induced EMF is E, partially completed bar chart. So, okay, so we have to just graph all the EMFs. For part A, what we want to do is we have E equals negative N, change in flux with respect to time. And yes, this is a solenoid with one loop, so that's just one. Or is it? Wait, no, it's absolute value, sorry. Absolute value, change in flux with respect to time. And that is just negative omega BA sine omega T, because that's a derivative of this. And that's absolute value function, so that's just omega BA sine omega T, right? And now you could just, because you have your T, you can estimate what your graph is going to look like for your induced EMF. So for time equals 0 to 1/2, it's going to be 0. This is going to equal this is for the 1/2 time. This is going to equal your time at, no, sorry, it's not 1/2, it's 1/4. It's going to equal your EMF at 3/4, and this is going to be 0. Yeah. Okay. B. Yeah, this is all based on the angle. If this omega equals 2 pi f. And if t equals, let's say 0, that's just sine 0, which is 0, so that becomes 0. At t equal 1/4 is the same as t equal 3/4, so that's going to be the same. This value of sine is the same, so that's going to be the same value. And at t equals 1/2, this just becomes sine of pi, which is 0 again. So, what else we got? Part B, yeah. Derive an expression for the maximum induced current in the loop. So, I mean, we pretty much did half of it. We have E equals your change in flux with respect to time, right? So we had E equals, and then E also equals I times R, Ohm's law. Then we had omega BA sine omega T, and then I times R equals omega T. Your I max is omega BA sine omega T over R. Okay, so let's check the variables. Okay, we're allowed A, R, B, and omega, but no T. That means this has a max value when sine is 1. So we're just going to cancel that out when sine is 1, so when omega T equals pi over 2. Okay, so the I max equals your omega BA over R. Yeah? That's your final expression. Part C. On the axis graph, instantaneous power dissipated. Okay, power is I squared R, right? So if you square that, well, of course, that's a function. Your current function is omega BA sine omega t over r, and then you square that. This part is just a constant. That's a magnitude. So this is going to be a sine squared graph, if that makes sense. This is going to look something like all positive. It's going to be a sine function, all positive. So, yeah, pretty much like that. Indicate whether the sketch you drew in part C is consistent or not with the bars that you drew in part A. Okay, so let's see, this is power with respect to what? Time? Okay. And as it goes up, okay, so how do we define this? Okay, power equals I squared R, which also equals V squared over R. And because both of these equations are related, power equals 0 when your EMF equals 0, so E equals 0. Therefore, the graphs match, because you can see that it's a sine curve that equals 0 when your EMF equals 0. So we have 0, it's 0 here, it's 0 at 1/2, but it's at its max at 3/4 and 1/4. So yeah, that makes sense. I mean, of course you're gonna write a more detailed expression, but it's like a